Yeah, thanks. Yeah, okay, so hello everyone and welcome to a continuation of Michal's department seminar. So he will be talking about symplectic Grassmannians, dual conformal symmetry, massive 4D n equals 4 superangulus particles, or amplitudes. Okay, so thank you. And the floor is yours, Michal.
Thank you very much. Let me... Okay, good. Thank you very much for introduction. And let me say a few words for the beginning. So some of you already attended my talk at the department seminar. So it will be, I will review some things, I will repeat some things, but many statements will be made much clearer, and I'll go much deeper into, for example, kinematics and also little group and the connection of the symplectic Grassmannian formula and in 6 dimensions, and the connection with the Yangian symmetry of massless n equals 4 and dual conformal symmetry, and so on. So you'll find some similarities, but don't worry, there will be new interesting stuff. Anyway, do not hesitate to ask anything if you don't understand or if you will see that something seems suspicious or weird or wrong. So do not hesitate to ask. Okay, so I'm going to present the work with my supervisor, Klaus Behring, and it's, let's say, trying to find the one very special formula for massive particles that describes scattering of massive particles in a one very special theory. But let's start from in a much more general way. So what are we trying to do is describe scattering amplitudes. So first of all, where scattering amplitudes arise. I think that probably all of you have already met Feynman diagrams and Feynman integrals. So at least at some basic course of QED or quantum field theory. So it's necessary to review all of it. But let me say a few words because amplitudes are really interesting part of physics, especially these days where some connections between amplitudes of various theories has been found. But what actually was at the beginning, the original motivation for amplitudes community to actually form, and that's a remarkable simplicity of some results. So as most of you probably know, if you want to calculate some processes using Feynman diagrams, it's usually very hard. Well, at tree level, at low number of external legs, it seems to be quite simple. Here is an example of number of Feynman diagrams that you need to take into account for gluons, so for QCD. And here you can see that for low numbers, you take low number of external gluons, you take a low number of particles. Low number of diagrams. So for gluons, you have just 4 diagrams. And they are simple integrals, you can evaluate them, and that's quite straightforward. But if you go higher in multiplicities, then the complexity rapidly grows. So for 10 particles, you have more than 10 million diagrams. But the answer or the result of such calculation is surprisingly simple. And if you use so-called spinor-helicity variables that I will describe on next slides and in next, let's say, 20 minutes, then you'll find extremely simple result that is long, probably like this. You can write it on a one line on a paper. So the result of summing 10 million diagrams, you can write it on a piece of paper. That's remarkable. So there is a huge cancellation. And this huge cancellation was actually the original motivation. Why should we try to find something, some new physics, new approach to calculate scattering processes other than Feynman diagrams. Because as we know, Feynman diagrams gives correct results, so they must be correct. But what if this is not the best way how to calculate scattering events and scattering amplitudes?
Yeah,
So
you should probably say this is for all n. It's not just n equals 10.
yeah.
N equals 10 equals 10 million. But
Thanks. This is for all n, as Klaus pointed out. This is for all n, for arbitrary n. N could be 10,000 or whatever. So this is quite really beautiful formula. But this is for tree level. What happens at loop level, for example? So at loop level, there appear some more complicated integrals, some loop integrals, and these loop integrals are usually divergent. What do we use in this case is some sort of regularization and renormalization. To regularize the integrals, we can use, for example, Pauli-Villar's regularization, or you can use dimensional reduction, that are, I believe, most common. And then you can renormalize your theories, so that's some procedure how you can get rid of infinities or how to make sense of divergent integrals. But if you start to go to higher loops, then you suddenly realize that they are more divergent and you have to introduce some more terms and so on. Okay, but for some very special theories, there is again something quite remarkable. For example, for n equals 8 supergravity, it is believed that it could be UV finite. So what it means is that all the ugly divergences in loop diagrams could cancel. That's something that, for example, happened for at least 2 and 3 loops. So that's other thing that could be quite interesting. And as a third example, there is something called double copy, which I'd like to probably tell more at the end if you'll be interested in. So there is something called double copy, which was found relatively, which was found, let's say, 10 years or more than 10 years ago. And that's roughly speaking statement that gravity is something like Yang-Mills squared, which is true at the level of scattering amplitudes, or it could be even true at the level of integrands. And it really helps to calculate scattering amplitudes in gravity, especially in amplitudes community, quite top modern thing is calculating post-Minkowskian and post-Newtonian corrections to binaries. So, for example, to calculate some corrections that are used to calculate binaries. So, for example, pair of colliding black holes. This is precisely the place where you use double copy, because you know how to find or at least describe scattering amplitudes of Yang-Mills to quite high multiplicity and to quite high loop number. And using the double copy, you can translate this into gravity side, and you can make corrections and predictions for post-Newtonian and post-Minkowskian corrections, for example, in binary systems. So that is, these days especially interesting because of LIGO, Virgo, and other gravitational wave detectors. So that's our basic motivation. Why to try find something beyond Feynman diagrams that would help us to calculate scattering events. Okay. So I'll be talking about some examples of formulas. I'll be talking about Grassmannian formulas. And let me a little bit jump to here. Grassmannian formulas are one of such possible ways which could give us some hint about the physics, about the other possible way how to describe scattering amplitudes. And it was discovered, or for the first time, It was used by a group around Nima Arkani Hamed, Jaroslav Trnka, and other people. And it's basically a very nice theoretical tool which led to discovery of positive geometries. And what do I mean by positive geometries? Well, that's attempt to interpret scattering amplitudes as a volume of some object. And this object lies in some auxiliary space, which is composed of momenta and other stuffs, twisters. But it was possible to see very beautiful things, and these days, at the original theory, it was discovered for massless n equals 4 super-Young mills in 4 dimensions. But today, there exists, and for this theory, there was discovered something called amplituhedron. That's the positive geometry behind the, well, people call it usually a hydrogen atom of 21st century. So massless n equals 4 super-Young mills. But these days, there are associahedron, permutahedron, and I don't know, many other hedrons that corresponds to different theories. So this positive geometry was also formulated for other theories. And it's a very powerful theoretical tool. But how about massive particles? Because all Grassmannian formulas and such, all of this beautiful geometrical interpretation as amplitudes as a volume of some polytope or some object. So far, everything was done just for massless particles. So what do we work on is try to find massive version of this Grassmannian formula. And the simplest case that seems to be doable, and most of you actually saw that is doable, at least for 4 points, is massive version of massive version of n equals 4 super-Young mills in 4 dimensions. So this will be the theory that you should keep in mind that we'd like to describe.
Does that mean that you are moving to the Coulomb rank of the...
Exactly. Okay. So for the online audience, there was a question if this doesn't mean that we move on to Coulomb branch. So yes. By massive n equals 4 on super-Young mills, we mean n equals 4 super-Young mills on Coulomb branch. Okay, so let me begin with some basics of kinematics. And in this talk, I'll mention several examples of Grassmannian formulas in 3 dimensions, in 4 dimensions, and in 6 dimensions. So let's start by describing what do we use, or what is used usually in the community. And it's very powerful, so it could be useful. Okay, so first of all, there is example of 3D massless. Yeah, I should stress one thing. We will, in this part, we will consider massless particles mostly. So the spinor helicity that I'll be discussing will be for massless particles. I'll make notes about massive particles at the end of this part about kinematics. Okay, so let's start with the simplest case, and that's 3D kinematics. In 3 dimensions, let's describe the massless momenta. So in 3 dimensions, massless momenta has how many degrees of freedom? So we have some 3 vector, and we want to describe, and we say that p squared is equal to 0. So that removes 1 degree of freedom, so we have 2 degrees of freedom. So in 3D, we have some p nu with 3 entries, but it should satisfy the relation that p squared is equal to 0. Based on some isomorphism, like that the spin group of Lorentz group in 3 dimensions is isomorphic to SL2R, we can actually find the spinor representation. So the ith momenta, where I denotes the particle number, we can write the massless momenta as a product of two spinors. And the alpha and beta are spinor indices that takes values 1 and 2. Okay, if we simply count the degrees of freedom, it works. This is two-component object, and here we have 2 degrees of freedom. So at least at this level, it works. Okay, and there is now one interesting thing, and that is called little group. So the let's discuss the little group, which we will think of as some group that actually preserves the momenta, that doesn't change the momenta. So in this way, where we write P as a lambda times lambda, the little group in three dimensions is actually very simple, is Z2, because we can change lambda alpha into minus lambda alpha, and it gives the same result. So in case of three dimensions, the little group is very simple. It's just Z2 or plus minus 1. Okay, that's probably all I like to say about 3 dimensions. So little group is Z2. Am I on whiteboard? Good. So let me use the blank mode. So let's move to 4D. In 4 dimensions, the P mu with as a 4 vector has 4 entries and has 3 degrees of freedom. And in this case, the decomposition is a little bit different. The massless momenta can be written as a lambda, alpha, and lambda I beta dot, where alpha is again 1 and 2, and beta dot is 1 dot or 2 dot. Okay, in this case, this is based on a little bit different isomorphism that spins the spin group of complexified Lorentz group in 4 dimensions is actually isomorphic to SL2C cross SL2C. Sorry, SU2 cross. No, that's 6. Yeah, SL2C cross SL2C. So that was the Lorentz group. Complexified Lorentz group, yes. So we consider also the complexified momenta. I'll make a note about the complexification of momenta a little bit later. For now on, let's think about P as a complexified momenta. So then the isomorphism that we use is actually between spin 4C and it goes to SL2C cross SL2C. So we have 2 types of spinor indices, alpha belonging to one of the SL2Cs and the alpha dot belonging into the second of SL2C. And now the little group is a bit more complicated, and it's actually U1, at least some part of little group, because the little group for massless particles is, I think, ISO D-2, but we consider just what's called homogeneous part of the little group. So this is in our case just U1. So what we can do is that we can rescale lambda and lambda tilde in this way. And this preserves the momenta. So if you think about little group as some group that actually that preserves the momenta, we can write it like this. Okay. Now, this is about 4 dimensions. Decomposition of massless momenta in 4 dimensions. And since we like to discuss something about massive particles in 4 dimensions, it would be good to say something about massive particles. So for massive particles, this decomposition is a little bit more complicated. And we have to add other pair of spinors, usually in the literature called nu. And there are some relations because this would be too much degrees of freedom. So
You want beta dot?
yes, thanks. Beta dot. So there are some relations among lambda and mu that gives m, and lambda tilde and nu tilde gives something called m bar. And in this scheme, for massive particles, we have this relation. So this is for quite general stuff where the mass should be, let's say, complex, but if your mass becomes a real, yes?
So the first thing is a scalar product and the second is a commutator?
No, that's also not exactly scalar product, but these are angle brackets. Lambda I and nu I is Lorentz invariant contraction of lambda spinors. Lambda alpha epsilon alpha beta, lambda I beta. And the angle bracket, lambda I tilde and nu tilde I, it's not a commutator, sorry. That's in the second sector. You know, we have SL2 SL2C equals SL2C. So you have one epsilon in one SL2C and the other epsilon in other. So here you have lambda tilde I alpha dot epsilon alpha dot beta dot nu tilde beta dot I. So that's basically the definition of what I wrote here. So the situation for massive momenta is a bit more complicated. You basically lost the beauty of massless decomposition because now you have here 2 more spinors, and this is, you know, this is the thing that has actually the beautiful geometrical interpretation. But if you add something, you naively lost it. And the reason why we go actually to 2 dimensions up is that we want to write this again as a simple decomposition of massless momenta. So therefore, to write this in a simpler way, we have to go actually 2 dimensions up. 1 dimension would be in principle sufficient, but since, you know, 5-dimensional kinematics is dimensional reduction of 6D kinematics, why don't go into 6 dimensions? It's more beneficial. So let's now discuss the 6D case. So in 6 dimensions, the situation starts to be much more interesting because the little group will be not that simple. Please?
Not that little.
Yeah, the little group is not going to be that little. So let's consider the 6 vector. 6. Again, with the condition that p squared is equal to 0. And what we can do now is that we use this decomposition. Where now A goes from 1 to 4, I mean capital A, and little a goes from 1 to 2. Okay. This is what I told you at the department seminar, but that's not true. Well, this is true, but it's not complete story. There is actually second part. Okay, but let me briefly make some comment on this. These indices, A and B, are actually so-called spinor indices, and in this case, this is based on isomorphism between. Okay, I probably forgot. Between spin 6C and SL4C complexified, which can be thought of as a SU4C. So now this index capital A belongs, let's say, to SU4. So therefore, it has four indices, and the little group is more complicated. In this case, it's actually SU2. And I is again a particle number which goes from 1 to n, where n is the number of particles. Okay, now I should actually mention how do we get from P mu to PAB. This can be done with the help of Pauli matrices. In 4 dimensions and 3 dimensions it was quite clear, but in 6 dimensions we have actually two possibilities. We can have PAB with upper indices and PAB with lower indices, which is usually called like this. And we can have lambda A tilde I A dot epsilon A dot B dot lambda tilde B B dot I. So there is, let's say, other copy. And why is that? That's because the little group in d dimensions can be thought of as a SO d minus 2. That's the homogeneous part of the little group in general dimension for massless particles, which in this case is isomorphic to SU2 cross SU2. So one SU2 actually corresponds to this A, little group index, and the other SU2 corresponds this to A dot, little group index. So the situation is a bit more complicated. We have actually two copies of, let's say, the same thing, or we have two possibilities how to express momenta. Now, it might seem to be quite puzzling, but there is quite a simple reason for this. Well, it's actually a mathematical obstacle, but there is quite simple reason for this. In 4 dimensions, you can define the angle brackets and square brackets just from two spinors, right? You can define this as a lambda, alpha, epsilon, alpha, beta, lambda, beta. Or say in other words, you can define this as a lambda with a lower index alpha. You can raise or lower single spinor index, but that is something you cannot do in 6 dimensions. Because here, in 4 dimensions, the isomorphism led to two copies of SL2C, where the invariant object is actually epsilon. So you could raise or lower single spinor index. But in 6 dimensions, the Lorentz group is isomorphic to SU4, where the invariant object is actually epsilon A, B, C, D, with 4 indices. So the reason is that you cannot raise or lower single spinor index. You can do just tuples of indices. You can find the relation that PAB is 1/2 epsilon ABCD P tilde CD I. So that's what you can find. So the situation is more complicated. But why did I? Okay, is everything at least a little bit intuitively clear here? I'd like to ask. If you have any questions, please ask.
So you said the spinor group at this level is
is SU4. The spin 6, comma C is SU4, isomorphic to SU4. C, of course, complexified. But the little group, in this case for D equals 6, of course, is SO4, which is isomorphic to SU2 cross SU2. That's the little group. Therefore, we have these two sectors.
Maybe another thing that maybe should be said is that the dimension of the spinners, this is vital spinners in various dimensions. So the vital spinner in 3 and 4 dimensions are 2-dimensional, but in 6 dimensions they are 4-dimensional. And that's exactly what the Michal is talking about. Vital spinner.
Yeah.
Sorry, can you say again what was the role of SU4 in the...
It's isomorphic to SU6.
To spin 6.
Okay. Is that the abstract symmetry of and it was for some relation?
Yeah.
But this has nothing to do with our symmetry so far.
Okay.
This is just kinematics. This has nothing to do with supersymmetry. I'm discussing the Lorentz group. The Lorentz group is SO1,5, you know, with the arrow up, let's say. And for simplicity, because you know then we should, to be precise, we should take into account all possible signatures. So to,
What does it mean? Because by the way, whenever you move to the Coulomb rank, you are not having SU4 as a symmetry anymore for the rate symmetry.
I'll get there. So this is so far Lorentz group, and we take complexified version of Lorentz group, which is you know, basically spin 6C. So in 6 dimensions, the situation is a bit more complicated. We have 2 copies of, let's say, the same thing, but at a department seminar, I mentioned just one. So the experts on 6D kinematics would immediately raise question, why? And the reason is relatively, I would say, pragmatic, because what we really wanted was to find something that would describe massive particles in 4 dimensions. And this has actually some consequences, because we don't not necessarily have to take into account full 6D kinematics. We, of course, first tried to find Grassmannian formula in the general picture, in this general picture, but we didn't succeed. We still don't know why actually it is not possible, but we tried many possible combinations of geometries and we simply didn't succeed. So the motivation was to restrict ourselves just to one copy. And you should immediately say, why is that possible? Why is it okay to take just one copy? And the reason, there are actually 2 reasons. First is Lorentz group and the second is little group. So from the Lorentz group point of view, although, yeah, I should probably write one more thing. So this is 4 times 2 object, 4 times 2 matrix. So we use the following embedding. Where lambda and mu you saw, I don't know, 10 minutes ago here at the massive decomposition. So this is the embedding that we use. And you can also write the embedding for lambda tilde. So what's the difference? A part of signs are different issue. The reason, if you really calculate, you can really calculate from Dirac equation, start from the beginning, find a solution to Dirac equation, and you'll find that your 4D spinners can be embedded into 6D kinematics in this way. What does it mean? Well, the difference is just that in this case you have a lower indices here, and upper indices here, and upper indices here, and lower indices here. So from the 4D perspective, it's just simple thing that you cannot raise or lower single spinor index in 6 dimensions. Okay, so let's define the theory in 6D, and deal with the fact that you have just one type of indices. You'll have only indices up or down. If you go to 4D, then everything becomes okay because you can use the 4D epsilon and you can raise and lower. That's the full trick. And the other thing is actually the little group. If you go into SO4, which is isomorphic to SU2 cross SU2, and you use this embedding and use something called helicity generators that are in both cases, then you can find that this will be identified into one SU2. Actually, when you use this embedding, then these two distinct SU2s, which naively seems different also for massive kinematics, but they become identical. Say in other, and this is the correct little group for massive particles in 4D, that's SU2. Before I told you that for massless kinematics it's U1, but for massive particles in 4D it's SU2. So that's exactly what happens, and that's exactly the reason why we can use just a single part, just let's say chiral model. And that's it. Okay, so that was one issue. So now we know how to decompose momenta in various dimensions. Okay, is everything clear here? Any questions? Please ask.
Maybe we should also say that the AB index is antisymmetric. And since this A and B is a 4x4 matrix, antisymmetric, so it has 6 entries in the matrix, and that corresponds to the 6 entries in the movement.
Yeah, so for online audience, Klaus had commented that this object is naturally antisymmetric. So antisymmetric 4x4 matrix has 6 entries, and which exactly matches the 6 entries here in the 6 momenta in 6 dimensions. So what I like to remember from you is that in various dimensions we have various decompositions, and in 6D it's a little bit more complicated than I will present. So that's one thing. Okay, let's now go to Grassmannians. So the Grassmannian can be, we can view the Grassmannian as some set of k-dimensional linear subspaces in n-dimensional linear space. So that's, say in other words, Grassmannian is a collection of all k-dimensional planes passing through origin in n-dimensional space. Okay, how is this connected to these kinematics? There is actually a very beautiful connection. Let's start with a simple example in 3D. In 3D, the connection is quite simple. Let's start with the decomposition. Lambda alpha, lambda beta, I. And let's add one more ingredient. Every scattering amplitude actually goes with momentum conservation. So every scattering amplitude contains some momentum conserving delta function times something. If it's super amplitude, there could be also super momentum conservation, super momentum conserving delta function, and then times some function of spinors or etas or whatever. So let's add these ingredients. Let's add momentum conservation. So sum of pi is equal to 0. So now let's rewrite this in this way: lambda I alpha, lambda I beta. And let's now define lambda plane without index, or capital lambda, with index I, alpha, sorry, where we arrange all lambdas, lambda 1, alpha, lambda 2, alpha, up to lambda n alpha. Then this is 2 times n matrix. So this can be simply written as a lambda transposed is equal to 0. Okay, but on the other hand, we can think about this as a two-dimensional plane in n dimensions. This is 2 times n matrix. So we can basically say that we have one n vector as a first row and a second n vector as a second row. So we naturally come to the geometrical picture of Grassmannian from this. This can be viewed as a 2 times n plane. So a part of the ordinary definition of Grassmannian, it would be good to...
Maybe you should tell what is the ordinary definition of Grassmannian.
I already told. That's the collection of all k-dimensional planes in n-dimensional vector space that pass through origin. So having this, thank you. So having this space, we can add some additional structure. And in this case, it's called the Grassmannian, which can be described by k times n matrix, equipped with this structure is called orthogonal Grassmannian. C belongs into O, G, K times 2K for some reason. So this is called orthogonal Grassmannian, and this naturally talks with the kinematics in 3 dimensions. And this geometry is quite important, will be quite important later. Let's move to 4 dimensions. Or is there any question? Okay. If not, let me continue. So the situation is a bit different, and it's different like this. So I add dot here, and tilde here. So that's the difference. Now we are at the level when the complexified Lorentz group was isomorphic to SL2C cross SL2C. So we have actually 2 planes. We have lambda plane up to lambda n alpha, and lambda tilde, which is lambda 1 up to lambda n alpha dot, tilde, tilde. And now the momentum conservation simply becomes this. Lambda times lambda tilde transposed is equal to 0. That's absolutely the same calculation as we did before. So the momentum conservation now is equivalent to this. Sum over I, Pi is equal to 0 is equivalent to this. That's just different rewritten. So now in 3D, in 4D, we actually have 2 Grassmannians, 2 different Grassmannians. Sorry? We actually have 2 different Grassmannians. We may have lambda or C, and let's call it C tilde transposed, and they should be equal to 0. Okay, and now C and C tilde actually belongs to different spaces, although it's not clear from this simple case. In this case, we have 2 times n and 2 times n matrix. they are orthogonal to each other, so it's quite reasonable to define C as a sum Grassmannian of K of the K planes in n dimensions, and it's quite natural to define orthogonal complement to the Grassmannian, which satisfy this condition. And well, the geometric interpretation is quite simple. If you have a two-plane, imagine, for example, I don't know, this table in 3 dimensions. So we have plane in 3 dimensions and the orthogonal complement. So you basically say take all the vectors that span this table and find a vector that is orthogonal to all these vectors, to this plane. So that's quite obvious that if you have this plane, the orthogonal Grassmannian is a line that is perpendicular to the plane. So that's it. So if you have K-plane in n dimensions, there naturally exists orthogonal complement, which is orthogonal to this Grassmannian. And that's exactly the kinematics that will be used in 4 dimensions. And this brings us where we want. This brings us to the 6D case. Because based on this analogy, we will find the Grassmannian in 6 dimensions. So the PAB is PA, little a, lambda A, lambda B, B, epsilon AB. Okay, but there is one small complication. What about this epsilon? It makes the, let's say, inner product between the lambda planes a bit more complicated. And actually it turns out that we can, if we define lambda plane A mu as a lambda A1I, so let's say 1 up to lambda A1N, lambda A2, 1 up to lambda A2N. So this is 4 times 2n matrix, and the spinors are written according to their particle number and little group index. So all spinors with little group index 1 first, and then the others. And then if you think about it as a lambda, then the momentum conservation becomes quite simple. Lambda omega lambda transpose is equal to 0, where omega is a symplectic matrix. 0, n times n identity, minus n times n identity, and 0. And if you realize that this is actually n times n identity times, and by this I mean Kronecker product of matrices, epsilon, where epsilon can be thought of as a 1, 0, 1, minus 1, minus 1, 0, then you actually realize that that's it. The identity matrix is, let's say, metric on the particle index. So, we don't use actually metric or particle index. We have just particle index in lower positions. But in principle, we could have. And what captures the little group in this case is this epsilon. So it gives this structure, and the momentum conservation can be written like this. And in this case, in 6D case, this is called symplectic Grassmannian. When moreover, your Grassmannian C which actually belongs to Grassmannian n, 2n. So it describes n planes in 2n dimensions and satisfy C omega C transpose is equal to 0. So that is called Symplectic Grassmannian or Lagrange Grassmannian also.
One comment, it's actually O times, not times.
O times. Okay, thanks. So this naturally goes into Symplectic Grassmannian for 6D stuff. So what I was describing here so far was absolutely general. There's nothing said about the theory. That's just about kinematics. This is absolutely general. So there is a deep connection between Grassmannians and the kinematics in various dimensions. Or let's say different Grassmannians and kinematics in different dimensions. And that's very deep. And I'll actually continue in this connection at the level of integral. Let me take a... Okay, so what I like to, was the message of this part is that we can associate some geometries in various dimensions with the momentum conservation, which plays an essential role in scattering amplitudes. So if there are no more questions, are there any questions? Is everything clear? Yes, Tanda?
So your lambda, which is 4 times 2n matrix.
Yes.
So to get, so that would be some element in the Grassmannian 4,2n.
Yes.
And Grassmannian is sort of collection of, let's say, planes or 4-dimensional things. So what sort of span series collection is it? Like all the possible lambda would generate all the possibilities for this plane. So because to me it seems like you're just one vector here. So what sort of spans the whole place? Is it like the all possible lambdas?
Yes. We should think about this as a quite generic matrix.
Okay.
We should think about this as a quite generic matrix, and then it describes the full Grassmannian for at least 4 times 2n.
I guess it's one point, it's a one kinematic state of your in particles.
And is it obvious that you generate all possible 4-dimensional planes by this plan? That it was standard full Grassmannian?
That is very closely related to, I think, gauge fixing that I will discuss later.
Yeah, I guess your question is that whether all spinners need to be used for different.
No, I mean the question is if there is enough spinners to fill the whole Grassmannian. That makes sense.
Yeah, well, I mean, first of all, you want to know if all of the spinners, I mean, a single spinner, if that can be arbitrary. And yes. That was the counting video from before.
Okay. Yeah, that makes sense.
Okay, thanks. But one thing, the map between momenta and spinners is not unique. It's like coordinate patch. You may have various patches, and you should think about it in a global way. Okay. Prezentace? So we saw this connection, and yeah, Nikki. And let's continue to some examples of Grassmannian formulas. So here are basically, is it also? So here are basically 2 main known examples of Grassmannian formulas that describe 2 different theories. One is in 3D, which is so-called ABJM theory. ABJM stands for surnames of these 4 guys. And that's a very beautiful theory in 3 dimensions, and it has Yangian symmetry. I'll tell you later what the Yangian symmetry is, but it's basically symmetry that arises by commuting 2 different algebras. One is conformal. This describes conformal field theory, and moreover, it has dual conformal symmetry. The same happens also for the massless n equals 4 super-Yang-Mills theory, and that's actually the first discovery of this Grassmannian formula by Arkani Hamed and collective. Let's for a second focus what exactly these formulas contain. There is some integral with measure, which is integral dc and some weird volume of GLK. I make a note. This will be actually very essential. It's also the same here. Then there is some rational function of minors. These brackets are minors of the Grassmannian. So minor is some determinant of columns of the Grassmannian. And then there is some, let's call it geometry conserving delta function. So this is exactly what's defined the orthogonal Grassmannian. And this is very closely related to the kinematics in the dimension. For 3D, we had the momentum conservation was basically statement that we have orthogonal Grassmannian. So we have the delta functions saying that the Grassmannian should be orthogonal. And then there is some delta function that makes connection between external kinematical data, which are the lambdas, and potentially supersymmetry, some supersymmetry parameters eta, and the Grassmannian. And the same, very similar situation happens also here, but this is common way how people write this in literature. So it's a little bit more secret. So here we have delta functions that actually plays the role of this delta function. So it's C times lambda. And then people say, okay, hey, C and C tilde are actually orthogonal Grassmannian. So they are related by this relation. But it can be again written as in this way, where the geometry is encoded in delta functions. So, therefore, we give this proposal for the formula. This is our proposal based on these observations and on a deep relation between kinematics and Grassmannians. So here will be some integral with measure, some rational function of minors, and this is very important. We should make some assumptions about this function. Then geometry, conserving delta function, which tells us that we work with symplectic Grassmannian, and some delta function that actually relates C and external kinematics. There is again omega, C omega lambda. Okay, so let's now for a second focus on this weird volume of GLN. What does it mean? Well, if you start to think about this formula without the volume of GLN, it's not here, then what happens is that you'll find that this integral is always infinity, is divergent. And it's very closely related to the phenomenon we know from gauge theories where we have to gauge fix and otherwise we would get infinities. So just by naive calculation, we actually find that we have here 2n squared integrations. 2n squared integrations, actually complex integrations. And how many delta functions do we have? So we have n times n minus 1 divided by 2 plus 4n delta functions. I just take bosonic delta functions. And by simple calculations and putting here numbers, you'll see that this is always greater. So you always have much more integrations than delta functions. So naively, there would be always overcounting, even for 4 particles where there should be actually no integration. Left. So the origin of this is actually in the geometrical picture. Assume that we have some k-dimensional Grassmannian. So this k-dimensional Grassmannian can be spanned by k linearly independent vectors, right? If you imagine a plane as a table, then you may have 2 vectors that span the plane, but also other 2 vectors, linearly independent, can span this plane. So there is actually a natural action of some transformations. You can consider some transformations that actually transform these 2 vectors onto other 2 vectors, or generally k vectors onto other k vectors. And there is a question, what is actually the symmetry group now of these transformations? Since we want to preserve the linearity, it's quite natural to assume that it's a linear group. So as a largest group, in this case, we should consider GLN, right? GLN, which are basically the n times n matrices that has non-vanishing determinant. So once having n-dimensional Grassmannian in 2 n dimensions, you can rotate these vectors by some GLN matrix. That's quite nice geometrical picture. Okay, but if you try to, this can be basically viewed that you define some other Grassmannian C prime, where this is 2 times n, 2n matrix, this is n times n, and this is n times 2n matrix. So this L actually belongs to this GLN.
Don't you want n times 2n first?
Yes, thank you. N times 2n. So let's now have a look how different parts of this proposed formula transform under this transformation. So the something what we call measure. So that's basically this D part transforms like this.
Do you want to see primes?
Yes, thanks. Delta functions now, those are basically just Jacobians. This is just coordinate transformation. So I'm explicitly writing the powers for n C prime omega lambda transposed now goes as a 1 over determinant to the 4th power of L, determinant of L delta 4, blah, blah, blah. Furthermore, there is Grassmannian delta function, which goes n times n, where the capital number is number of supersymmetries. C prime omega eta transposed goes as determinant to the power of n of L delta n times C omega eta transposed. And the last is, okay, let me erase this thing. Delta n times n minus 1 divided by 2. C prime omega C prime transposed goes as 1 over determinant to the power n minus 1 of L and delta n times n minus 1 divided by 2 C omega C transposed. So under such transformations, every individual part of the proposed formula transforms with the determinant. So naively, why we shouldn't just consider SLN invariants? Because in case of SLN, all these determinants are simply 1. It would be much easier. Because, you know, I told you that we have some transformations, and I immediately say, okay, the largest group is GLN. But why? Why do we really want GL? And it has actually very deep connection to something called dual conformal dilaton. Because this is purely geometrical thing. This has purely geometrical interpretation from the Grassmannian picture. You just think about the Grassmannian as an n vector as an n plane into n dimensions, and there is a natural action of GLN. But why do we really want GLN? Because if we would consider just SL group, then these determinants would be 1, and there would be basically nothing. They would be automatic. But if we have GLN here, then it actually gives us one more powerful thing, because we find what's the weight of this function. We want this integral to be invariant. That's exactly what happens also in gauge theories when we integrate over gauge fields. When we integrate, in path integral over gauge fields, we naively overcount, and we would get always infinities. And we should pick a specific gauge. And that's exactly what means also here. Yes?
So by weight you mean the power of the determinant which it transforms with?
Yes, exactly. So by weight, Standa was asked if the weight, I mean the power of determinant that the function should transform with. And that's exactly what it means. So that's very similar to what happens in the QFTs, in gauge theories, where we also have to gauge fix. So in this case, gauge fixing is represented by this volume of GLN, because we can use this GLN to gauge fix some part of the matrix, for example, to some numbers, right? It could be orthonormal basis or something. So this is purely geometrical, but already the gauging appears also here. So also here we should sort of gauge fix this, because one configuration, which is one Grassmannian, can be described in many ways, and we should get rid of it. Okay, so now remains question actually why GL, and I'll leave it open for a few minutes. And actually the result is that the function here, f(6d) of C should C prime, should transform like determinant to power 3 minus small n minus capital N L f(6d) of C. That's exactly the weight you asked. That's the power that the function should transform with. For our case, we want to consider n is equal to 2, capital number of symmetries is equal to 2, and small n we will mostly focus on 4-point example. So in our case, the weight will be minus 3. Okay. So this has actually very nice interpretation, and actually we already started to fix this function f. This function f is actually the only thing that depends on the theory. That is the only thing that is theory dependent. And by simple thinking about this structure, we immediately find that it should have some weight. If it consists of determinants and has rational structure, then it must have certain weight. For example, minus 3 for 4 points. Okay, what can we deduce more about this function? without losing a small amount of, let's say, work. So other thing that we can use is the little group. We already discussed little group. The little group is some group that leaves the momentum invariant and that removes the auxiliary degrees of freedom in lambdas. Because naively, these lambdas contain more degrees of freedom than the momentum needs. And the little group is exactly what removes these auxiliary degrees of freedom. But that we discussed for one particle. How about more particles? If we have more particles than one, the situation is a little bit different.
Can you write below shadow on the whiteboard? There is a shadow.
Okay, below here. Thanks. So, what do we want now is to consider a little group for all particles. For if we have n particle scattering, then for all n particles. And we should actually think about it in this way. We need to remove the auxiliary degrees of freedom from spinors for every particle. Therefore, we actually need for every particle its own little group. Therefore, if we have n particle scattering, then I is equal to 1 up to n of SU2. We actually need n copies of SU2 somehow arranged into a matrix. And what you commonly see in literature is that this belongs to USP2n. This group is much, much bigger. This is intersection of unitary group in 2n dimensions and symplectic group in 2n dimensions. Okay. Here could be a nice argumentation why actually we need USP, so unitary and symplectic. Because naively, symplectic would be enough. Because if we can write the overall momentum, it's lambda, omega, lambda transposed. So naively, we can make some little group transformation in this language. Yes, no, P. That's P, lambda times lambda. Lambda has the mass dimension 1/2. So naively, we can make a little group transformation in this way, right? Where M is in USP2n. That guarantees that it's okay. So P prime then could be lambda prime, omega, lambda prime transposed, which means that this is lambda, M, omega, M prime, lambda prime, transposed. And if we say that this is omega, then we are okay. We have the little group. That preserves the momenta, right? And that's exactly how symplectic part appears. But how about the unitary? For those who work in this business, it's very natural it's sometimes people very freely go between real and complexified momenta. If you want to work with complexified momenta, forget about the U. It's not necessary. You just need symplectic part. If you want to work with real momenta, you really need USP. The unitary part of the group preserves the reality of the momenta. Otherwise, this is over C, of course. Otherwise, you just need SP. And that's also the case of SU2 in the little group. Naively, you have just epsilon tensor that's exactly the same. You have just epsilon tensor that you need to preserve. And that's simply symplectic group, not SU. But if you want to preserve the reality of the momenta, you need this. Okay. So we already discussed how this happens. So the little group transformation can be viewed as this. And this actually, how actually this change? Delta C omega C transposed, delta C omega lambda transposed. So the little group is transformation on lambdas. So let me write this prime. So let me transform here. What it actually means for C's. For C's, okay, so let me write this again. C omega C transposed, delta C omega M transposed, lambda transposed. Now, we should like to have this actually little group invariant. There is some actually result that from the massless n equals 4, from massive n equals 4 super Young-Mills that the amplitude should be, the super amplitude should be little group invariant. This is our external input. Sorry, I don't have actually enough time to explain why, but the super amplitude should be little group invariant. Therefore, we want this also to be little group invariant. That's our external data, let's say. That's our external information. So what does it mean, for example, for this? Well, we can do one trick. We can insert here M transposed M and do also the same thing here. M transposed and put M and M transposed here. So what we did is that we redefined C. And let's denote this as a C prime. C prime to be M times C. So this is our new C. I'm actually doing just coordinate change, but in the reverse order than I did before. So then I have C prime omega C, because this is actually invariant. Nothing happens. I can write omega in this way. Oh, sorry. Just like this. Because this is the relation for M, that M is symplectic. And the same, sorry, I screwed up a little bit. I can insert M here. So this gives us delta C prime omega lambda transposed. So what it means is that this doesn't change. The question is, how does this measure transform? Well, the measure again transforms with the determinant of this matrix M. But since it's symplectic matrix, its determinant is +1. Therefore, it doesn't change anything. So this function must be invariant under such change of coordinates. And we actually haven't specified too much about the theory. We just said that the super amplitude should be invariant under little group transformation, which is quite natural assumption for super amplitude. So this has consequences for minors. Okay, let me speed up a little bit because I think I'm quite running out of time already. So this has consequences for minors because the function f of c is should be composed out of minors, and it should be invariant under this change. So what it does is basically that it fixes the entries, half of the entries. So it quite rapidly decreases the number of independent brackets, of independent minors. Okay, so far these were just kinematical assumptions, nothing more, and we were able to say quite a lot about the function. And all of this is basically true also in general. So this is very strong connection between Grassmannians and just kinematics. Now, how about the theory? So, what do we get from theory are symmetries. And now we'd like to apply symmetries to this example. And we have quite beautiful structure here. Because for massless n equals 4 super Young mills, there is a very nice structure called Yangian. And this Yangian comes from two algebras. Conformal algebra and dual conformal algebra. I can show you actually how these algebras look like. I can show you explicit representation of these algebras from the original paper where the Yangian algebra was discovered. That's it. Can you see at least something? Almost not. Is it at least a little bit better? Oh, not that much. Oh, plus. Okay. Thanks. So this is standard conformal algebra. For those of you who ever seen, the conformal algebra, which is algebra that preserves angles. Then we have this is actually super conformal algebra. So the conformal algebra is just this part with the dilaton. And the super part of the algebra is here with the central extension. This is actually PSU 22/4. But this is the conformal part. That's quite standard thing when you meet CFT, when you have conformal field theory. And this is in the so-called on-shell space. Now, you can define the dual space that I was talking also at the presentation by simply writing every momenta as a difference of 2 points. Now you go into these coordinates and you'll find something very interesting. And that's exactly what's this paper about. This paper is about finding a dual conformal symmetry, which in dual space is represented by these much more complicated generators, where you can see, and also for super momenta, you have theta I plus 1 minus theta I. And you'll find that there exists another conformal structure, actually super conformal structure. This is in this dual space, in axes and thetas. And that's this dual conformal algebra. This has absolutely nothing to do with the conformal algebra. That's something else. That was a huge discovery in 2009. And the interesting thing is when you actually bring these two algebras into same space. Because here the generators are in terms of axes, but here in terms of lambdas and p's. So what happens is that these quite complicated generators, but non-local generators, become even more complicated, but can be very, very easily written. And that I'd like to go back to my presentation. So this is the example of one important dual K generator that in the on-shell space can be written like this. Or like this in 6 dimensions. Some non-local, quite complicated formulas. And what this gives rise to is that if you start commuting in on-shell space, where is the thing for erasing here. If you start commuting generators of this dual conformal algebra, you get new generators. And if you commute also with them, you get also new generators. So these are so-called level 0 generators, and these are so-called level 1 generators. And you can get level 2, level 3, up to infinity. You actually get infinitely many generators. You get a structure called Yangian. And this is the reason why n equals 4 super Yang-Mills is actually believed to be integrable, because there exists this Yangian structure when you have infinitely many of these generators. And this has very strong implications for the Grassmannian formula. So if we start to think about the Grassmannian formula again, then we find that for massive n equals 4 super Yang-Mills, there is no conformal symmetry. It cannot be conformal. By introducing mass, we actually introduce some scale, and that if in the theory is some characteristic scale, it cannot be scale invariant. So that's actually something that breaks the conformal structure. So you cannot have Yangian anymore. And that's what people thought that could break the integrability. But recently there has been discovered some other possible structures.
So you break the conformal symmetry on the level of 4 dimensions or in 6 dimensions?
Both. In 4 dimensions, the argument goes that you introduce mass, therefore you introduce some scale. But there exists some, let's say, pattern of theory, which is called n equals 1,1 super Yang-Mills in 6 dimensions, whose dimensional reduction you get also scattering amplitudes of massive n equals 4 super Yang-Mills. But this theory has other problem because its coupling is dimensionful, is not dimensionless. Therefore, again, the problem with the scaling is not. Therefore, you break the conformal symmetry and you lose the Yangian structure. It cannot arise anymore. But what is more interesting is that these massive amplitudes and also 1,1 super Yang-Mills in 6 dimensions has dual conformal symmetry. It stays preserved. It's still there. And let me schematically write the 4 generators. It's actually, there could be more. For example, Lorentz generators, if you have in 4 dimensions, you can have M. You can have M and M bar. But basically, you have these 4 in conformal structure. So this is actually preserved. And this is one of them. This is the dual K. This is the dual K generator. So what to do now is to apply this generator on the ansatz that we have. And what we already know is that we have d2n squared c divided by volume of gln, then some function delta c omega c transposed, delta c omega c lambda transposed. And we already know quite a lot about C. We know that it's composed out of minors that has this form, I plus n, j plus n, purely from kinematics. And it has a rational structure. That's our assumption, actually. And we know the form of these determinants. So we know quite a lot. And the last missing ingredients is actually information from this algebra, so from D and from K. And probably the last thing that I want to mention today is that although these formulas are beautiful, those who attended the seminar already know that they cannot, this Grassmannian formula is naturally conformally invariant. And that's because if you can write it in a very compact way and well, know how to argue in the simplest way. let me make a statement that this is naturally conformally invariant. So this type of formulas cannot be used cannot be used to describe massive amplitudes of n equals 4. So why did I spend 1.5 hours of your time by describing it? That's very simple. Because we have to modify our ansatz by some inner product in here. That's basically the difference between massless and massive amplitudes. And the origin is in the fact that we do not have this dilaton invariance, which naturally talks with this structure. But we have dual dilaton. There are two different dilatons. We have dilaton in the conformal structure and in the dual conformal structure. And now, in a massive case, they do not match. They are not identical. For massless n equals 4, they are identical. And that's actually the reason why conformal and dual conformal structure can talk together. In this case, in the case of massive amplitudes, they do not match. So they cannot be symmetries of the massive amplitudes simultaneously. There is quite a nice reason why, actually, but I don't think that I have enough time to discuss. So the reason is that the dual dilaton now is the symmetry, and it gives us the different counting. Therefore, for the amplitude, therefore we have to introduce some auxiliary weight depending on the momenta. And now we can apply K. That's information from D that we should add some inner product. And the information from K is that K is actually what fixes these numbers here, I and J, and powers. By simple acting of K on the Grassmannian formula and doing some manipulation, this actually fixes these numbers. And I skip some details and show you just the result. So this is the result of the calculations that we did of the applying all the dual conformal assumptions to the amplitude. And it's quite complicated formula, but it exists. And it's first Grassmannian formula for massive particles, and this describes massive scattering amplitudes of n equals 4. So let me stop here, basically. So although I discussed a little bit different things than on the seminar, and this last part was quite maybe incomplete, I hope that I convinced you, at least at a general level, that the Grassmannian formulas are quite nice and naturally talks with kinematics and could be used as an alternative description of scattering amplitudes. And at the level of symmetries, although the calculation is quite long, those amplitudes could be found, and the formulas, we hope that it will lead for some analogs of amplituhedron like geometry for massive particles, or positive like geometry for massive particles. Okay, so that's all from me. And before questions, I'd like to say one more thing. And that's that if you'll be ever interested in, okay, I probably forgot to copy it, sorry. That if you are interested in this stuff, in scattering amplitudes or in double copy in scattering amplitudes or so on, and you'd like to talk with some people that are, in this business, next summer in 2022, there will be Amplitudes Conference, which is the annual conference in the Amplitudes community, and it will be held in Prague. And with Klaus, we are co-organizers. So if you would like to join this conference, which is something about 200 people interested in scattering amplitudes, and speakers like Nima Arkani Hamed, Jaroslav Trnka, Lance Dixon, and other big names in not only in scattering amplitudes, but also in physics generally. Also Zwieberg, for example, Lionel Mason. Then you are, of course, welcome. And before the conference in August, there will be also summer school. So the summer school is usually for 1 week long, and there are 4 main topics that will be taught. So it's quite, I think, quite great opportunity for people here, you know, because from Brno to Prague, it's very easy to go. Okay, that's all from me. Any questions?
Yeah. So, do we have any questions? So, supersymmetry plays no role in that story.
In what? So the question was if the supersymmetry plays or doesn't play any role in this business. I'm repeating for online audience. So.
Because whenever you move from the origin to the Coulomb branch, you are in this case, then it was important you are preserving some supersymmetry. So the reason because you are having this structure is because you have some supersymmetry behind on something that doesn't depend on that supersymmetry content.
That is a very good question, and I basically omitted almost all about supersymmetry. The procedure, like was presented here, or rather was not, almost doesn't depend on supersymmetry. The first argument is that because we use just dual conformal symmetry. So although you may have some, in our generators, you may have some etas as a Grassmannian parameters, their indices are always contracted. So we use only generators that do not have external Grassmann indices, Grassmann odd indices. Therefore, whatever the R symmetry is, it actually doesn't play a role in this game. That's one argument. The second, so we use only generators that are not affected by the R symmetry. Another thing is actually that we are doing something a little bit weird. We are describing a non-chiral theory, which massive n equals 4 on Coulomb branch is described as a non-chiral theory. You take your eta, which is, for example, eta 1, eta 2, eta 3, eta 4, and you have Grassmann Fourier transform 2 of them. For example, these two into eta tilde 2, eta tilde 3. And then the parameters that you use are these. And what we are doing is that we are embedding these into the chiral version in 6D. It sounds weird that we are describing somehow non-chiral theory in terms of chiral theory. But again, the argument is that we do not use R symmetry. Therefore, this is okay, and as a formulas, it works. But when we would like to start working with something with R symmetry, it will be a problem. Moreover, for massive n equals 4, naively, the R symmetry is SU2 cross SU2. Because, as you know, massless n equals 4 has SU4 R symmetry. And this should go into SU2 cross SU2. The problem is that this is not true. There are some reasons when there are some obstacles which actually tells us that we can have a little group manifest or R symmetry manifest. And the common way how to describe amplitudes on the Coulomb branch is with manifest little group symmetry. Therefore, actually, even at the level of amplitudes, of calculated amplitudes, that are 4 and 5 point super amplitudes, not amplitudes, you can see just U1 cross U1 part of this SU2 cross SU2. And this is exactly because we cannot have both R symmetry and little group symmetry manifest. And the people usually choose little group manifest and the R symmetry not manifest. So there are much more issues. And this is exactly also a reason why we can use this, let's sort of say, unnatural embedding when we describe chiral theory, non-chiral theory in terms of chiral. Because we can use just this U1 cross U1.
So you gain nothing by changing the rule, like, okay, you would like to preserve R symmetry and you don't preserve the little group, so you will get same, just you are like risking simplicity of the computations or something?
It would be much more difficult, actually. Because, when you... At this level, the only place where Grassmannian parameters appear, or Grassmann coordinates appear, are in the delta function. And that's also true for amplitudes, not only Grassmann, but amplitudes. And with not manifest little group, all these things become much more complicated. Actually, from the amplitudes point of view, it makes much more sense to preserve the little group, because then you can easier extract the real amplitudes. And the amplitudes is not super amplitudes. Amplitudes as such are actually transformed under little group. What makes the super amplitudes not transforming are exactly these Grassmann parameters, that these Grassmann parameters capture the little group transformation of the amplitude in some way. So it's better to, in this language, to keep the little group invariance manifest and sacrifice a little bit of the R symmetry.
One last thing, or I don't know if somebody will ask me, so maybe I can use. Okay, you said something about 60 n equals 1, 1.
Yes.
Can you elaborate more on that, the relation that you put your theory of 60 and this n equals 160?
So there was question if I can elaborate a bit more on 1,1 superangles in 6 dimensions.
The relation, I mean, not the theory itself, it's the relation of the stuff you were discussing with that thing, because I'll tell you where I'm having in mind, like, whenever you move this thing from the gravity point of view, of course, whenever you move to the Coulomb branch, it's like you are having, this stack of detribranes, and you are separating all detribranes, and that's why you get the mass. And
yes.
Then you break conformality. That's basically the picture somehow. So, what is the relation between that picture, if there is any relation between that picture and the 60 n equals 1, 1 thing? Because basically you are in that Coulomb rank whenever you move the branes in the geometry picture. And the 6D n equal 1 will have some kind of relation because you sort of say that it is related to the 4D stuff. So can you say something about that, or is just like beyond the thing that you can comment?
What I can comment on is that the amplitudes of 6D 1,1, if you write the amplitudes of 6D 1,1 theory, and then you do the dimension reduction, you get exactly the massive n equals 4 on Coulomb branch. So you get precisely these amplitudes. And it has also exactly the same symmetries. So if you want to really do it in a correct way, also with the asymmetries that I've been discussing here, that's the right theory. But we were not able to find non-chiral version of Grassmannian formula. So that's actually the reason why we use chiral model. From your perspective of having stack of D branes separated by some distance that corresponds to mass, the n1,1 is absolutely that's the right thing that you should think about. But what we are using is rather for pragmatic reasons. And that's also the thing with the, well, there is also another issue, because when you use this model, also the correct Lorentz generator is lambda I alpha d over d lambda I beta. minus trace, where these parentheses mean that it's symmetrized. But when we work in our model, let's say, we should be a little bit careful because this symmetrization is not there. This symmetrization comes from these two copies. There are certain issues that we should pay attention. We are not actually. Our model covers all the amplitudes of n equals 4, but maybe not all of them, and we are pretty sure that not all of them. Because we are, for example, not able to construct odd multiplicity, amplitudes with odd multiplicities of external x. And that's just because of the 6D kinematics. We are not able to construct it. They exist, but we cannot see them. So our model works in 6 dimensions, and but this is just model. But the procedure that we used to find the amplitude, it's independent of this. The full thing can be redone in 4 dimensions, and then we can find everything. Also, it will work with the R symmetry, and the Lorentz group will work, and we can find odd multiplicity amplitudes, and we can use actually factorization and other stuff. So this was just model where to test this procedure, how to find Grassmannian formulas for non-conformal field theories with dual conformal symmetry. And it seems that dual conformal symmetry is pretty strong and works for a large variety of theories. So yeah, we use a little bit weird model that probably is not very suitable for what you're talking about the brains and stack of d-brains. The right thing is n1,1 superangles in 6 dimensions. But for pragmatic reasons, we choose this model. Any other questions?
So is the result at the end like you're finishing thinking of physics, or are you trying to use it to calculate some amplitudes?
You mean?
Like figuring out the...
Do you mean this?
Yeah.
Well, we are very, very happy that there is at least something, that we found at least something. But this is actually the best we could find in 6 dimensions. Because to go further, well, 4-point example is special. Because we have as many integrations as delta functions. Therefore, the integration is completely fixed. Even after gauge fixing. But for higher legs, there are actually some integrations left. And they have to be taken care by appropriate contour. Because these are contour integrals actually. So we have to find contour. To find contour, we could use 2 ways. A, explicit form of calculated amplitudes for Feynman diagram, from Feynman diagrams. But the problem is that massive n equals 4 on Coulomb branch is that so complicated that we know just 4-point and 5-point amplitudes at 3 level. We don't know anymore. And some, those are actually super amplitudes. And some amplitudes, this means some sectors for 6 points. So in order to continue in 6 dimensions, we would need to 6-point amplitude, which is not known. Therefore, that's not the right step. Other procedure, how to find, for example, 5-point and 6-point amplitudes would be the factorization. Scattering amplitudes must factorize in correct ways. So if you go, for example, if you have the S-channel diagram, for example, and you put this like on shell, then it should go like 2 3-point amplitudes, and here is something like 1/p². The transfer momenta here. So there are some factorization requirements. That can be used in 4 dimensions. That would be a natural way how to continue. And there are, of course, many other issues, many other ways what to... So this is basically the end, and I'd like to finish here, the PhD thesis. But there are still many open questions. For example, what's the contour? What's beyond, 4 points? But the procedure that describes this is suitable not only for this theory, but also for any other theory which doesn't have conformal symmetry, but has dual conformal symmetry. And the other thing is that I'm talking still about conformal symmetry. And the question is, what about superconformal symmetry? People usually say that there is no superconformal symmetry, rather some enhanced super Poincare, because the Q, for supersymmetry you have Q and Q bar. And Q bar, anticommutator, should be something like P. Q is a symmetry of superamplitude of massive, but Q bar is not. But actually, we can modify this Q bar such that we subtract what breaks the supersymmetry, what breaks the invariance, and it doesn't change this commutation relation. So we can enhance this generator. And now, question arises, what happens to the rest of superconformal algebra? Because we can use some relations where conformal inversion plays a role. So the question is, what about this? If we modify the Q bar, then we can define this generator that annihilates the amplitude. But what's the structure? And we don't know yet. We haven't calculated the supercommutator yet. So this would be another stuff where to continue. But I think that I hope that this would be enough.
Any other questions?
Okay, no further questions. Any questions from audience? Or online audience? Okay. Thank you.
Okay, so next week we'll have Yes, so thanks everyone for participating, and next week we'll have Darek Cidlinski speaking about something very simple, because we are thinking it's the last seminar of this year, so let's have some very basic topic. So we'll be talking about Bernoulli numbers and some sums, so just something interesting from mathematics. So feel free to come, and also feel free to invite any bachelor or master students, because it will be quite understandable for everyone. Okay, so thank you again, and see you next week.